we're going to continue discussing entropy. I don't have a lot of voice today, so don't make me speak too much. But well, we need to talk about relationships between thermodynamic properties, including entropy, that come about from what we have learned so far about the first law and the second law. So these are called thermodynamic property relations. They are in the same chapter, the same entropy chapter that we have been discussing, which I guess is chapter 5. So if we, let me just take some of these here. If you, for example, if you take the first law, you write the first law for a system, for a closed system. We know that we can write delta U equals Q minus W. But we can also write it in differential form. So we can write the differential form of this would be du equals delta Q minus delta W. All right, so that we can write from the first law. We also know that we can write the expression for work, so we can write dW as P dV. And we just learned this week that if a process is reversible, we can write that the heat transfer is equal to the product of temperature times the differential change in entropy. But that's only for a reversible process. That comes from the Clausius inequality. So we can say that this comes from the second law. So we write down the first law, we write down an expression that comes out of the second law for a reversible process, and we write down this expression that we already knew for the calculation of work. So if we put everything together, that is, we take this expression for the work and put it in here, and take this expression for the heat transfer and put it in there, then we arrive at du equals delta Q, which is TdS, minus delta W, which is P dV. We arrive at that. And that is, in fact, a thermodynamic property relation, because everything that you see there is a property. Internal energy. This is written extensive, but let's write it intensively. So if I divide by the mass of the system, then this becomes lowercase u. This becomes lowercase s. And this becomes lowercase v. So everything there is now an intensive property. Internal energy, temperature, entropy, pressure, and specific volume. So it is what we call a thermodynamic property relation. Not only that, even though I derived it using a result from the second law that is only valid if the process is reversible, because my result doesn't depend on the path. So if I have a variation of properties from an initial state to another state, or even an infinitesimal variation like the equation implies, everything that appears there is a thermodynamic property. It doesn't depend on how you go from one state to the next. Therefore, this is actually a thermodynamic property relation that is always valid, despite the way in which we derived it. So all are intensive properties. And therefore, that allows me to conclude that this is always valid. And that's our first property relationship. We can get a second one if we do the following. So if I now bring in, you remember our friend enthalpy. So we know that the enthalpy is defined as internal energy plus pressure times specific volume. So if I take this and modify it a little bit in a way that I can make a substitution into this first relationship, then I can get another one. The way we do it is, since what we see is a differential internal energy, we want a differential internal energy here. So first, let's solve for the internal energy. So U is H minus PV. And now let's go ahead and differentiate this. So let's do du, simply differentiating, is dH minus the differential of the product of P and V. So you just apply the product rule. You do, say, for example, P dV, the first times the differential of the second, and then the second times the differential of the first. Right? Simply differentiating and using the expression for the derivative of a product. So if I now take this and put it back into my first property relationship, I'll get a new property relationship. So let's do that. Let's replace this du with all of this. So we have dH minus P dV minus V dP equals T ds minus P dV, right? And then notice that this term minus P dV appears on both sides, so I can cross it out. And then I have that dH is equal to T ds, and then the remaining term here, if I move it to the right-hand side, VdP. So here is a second property relationship that is very useful for us. Again, just like the first one, it only involves properties. So this expression then is independent of the path that is being taken by the system, and therefore that expression is also always valid. So these two, it's right here, always valid, are the two property relationships that will be very useful for us in doing calculations. Because usually they help you find a missing property or the variation in a missing property if you know the variation of some other properties during a process. Say, for example, that you take a substance that is incompressible. So, for example, for an incompressible substance, for example, if you're dealing with a system that is a solid or is a liquid, and you may make the assumption that it's incompressible, then if you take a look at the first of these relationships, right, during a process for something that is incompressible, what can I say about the first equation, the first relation? There will be no variation in the volume because it's incompressible. So if I take the first one of these, then I can say that du is equal to T ds. Right? Because I ignore the variation in the volume. I'm assuming that it's incompressible. Then I can use this relationship, for example, to find, if I solve for the entropy, ds is du over T. And I can use this relationship to find the entropy change if I know the variation in internal energy. But again, the relation is in differential form. So if you really need to find the change from state 1 to state 2, you always need to integrate these relationships because they are written in differential form. So if I integrate from between 1 and 2, the integral of ds between 1 and 2 will be delta s, or s2 minus s1, by integrating. Right? And then I see on the right-hand side that this is going to be then the integral from 1 to 2 of du over t. Simply integrating the differential form of the expression between states 1 and 2. And now we learned when we learned about specific heats, we learned that we can write du for such a substance, for an incompressible substance, as the product of CV or C, because it's an incompressible substance. We don't make a distinction between CV and CP, just a heat, a specific heat. So we can write this as integral from 1 to 2 C dt, because that's what du is, over t. And now it's getting to a place where we can almost finish the problem if we make one more assumption about the specific heat. What can I assume about the specific heat to make our life very easy? Assume that it's constant. So if I assume if C is approximately constant, then I find that this entropy change that I am looking for this incompressible substance is C natural log of T2 over T1. I find this useful result. So if I have an incompressible substance and I assume that the specific heat is constant, then I can find the entropy change, delta S, for that substance as simply the product of the specific heat times the natural log of the initial and final temperature. So that's all I need to know. Suppose you have a solid, assume that it's incompressible. You want to find the entropy change for a process in which it goes from temperature 1 to temperature 2. That's all you need to know. Initial and final temperature, take the log, natural log of the ratio, multiply times C, that's your entropy change. And this also tells you something interesting, because if a solid or any incompressible substance undergoes an isothermal process, then what happens to the entropy? Solid, so incompressible, isothermal. Which means that what kind of a process is it? It's isentropic too. So that's just an interesting fact, an interesting result that comes out of this relationships when you apply them to an incompressible substance. That if it's isothermal, it'll also be isentropic. It happens to be both. That it will only apply under those conditions because that came about because we were able to neglect the PDV term. We don't do a whole lot of things with solids. It's more interesting for us to deal with gases. So let's see what happens in the case of a gas. So let's assume that we're dealing with an ideal gas. So that was an incompressible substance. Now let's do an ideal gas. Let's see what happens. So let me write down the first of the relationships that we derived, this one. I'm going to rewrite this one, but I'm going to rewrite it in terms of the TDS. So it'll be TDS equals du plus P dV. That's the first relationship. Right. So let's do the same thing. Let's try to use this to find the change in entropy. So I have an ideal gas that goes from state 1 to state 2, and I want to find how much the entropy changed during that process. So I can take this and solve for the entropy change. So divide by the temperature. Then we get ds equals du over t plus p over t dv. Notice that also this is not too different from what we just did for the incompressible substance, but now we're carrying an extra term because the specific volume will change. It is a gas, so it has great ability to compress and expand. All right, so I have that, but I can make some substitutions. I can make a similar one for the first term, because we know that for an ideal gas, du is which specific heat? Is this a V or is this a P? Is this a V dt? I know that for an ideal gas. I can write that here. Ideal gas. And I know that P times V is RT, also for an ideal gas. So these two expressions we knew from before because they apply to an ideal gas. So let's use them both. Then we get ds equals Cv dt over t. And then P over T is R over V. So R dV over V. And then you can see how by combining expressions that we knew for ideal gases, we managed to put the functions in a way that we can integrate them. So if I now, again, say I'm looking for the total variation from 1 to 2, so I want the delta S, and I integrate, and I find that delta S, which is S2 minus S1, is going to be the integral from 1 to 2 of Cv dt over t. Right? We can decide what to do about the Cv later. But the second term, there is nothing to decide because the R is constant. So I can take it out. And then I have the integral of dv over v, which is a natural log. So I get natural log v2 over v1. Right? So now I get this as a way for me to find the entropy change of an ideal gas. But now I need to know the temperature variation, and I also need to know the volume variation. If we now go ahead and make the same assumption as before, so if we assume that Cv is constant, which we can make many times in many problems, then I can go ahead and integrate like I did before. So if I make that assumption, then delta S becomes Cv natural log T2 over T1 plus R natural log of V2 over V1. And that's a useful expression. It allows me to find the entropy change for an ideal gas if I know how much the volume changed and I know how much the temperature changed. So if I know those two things, those two variations, then I can find the variation in entropy. Okay. Similarly, and I won't go over the whole development because it's very similar, if I start out with the other relationship, so here, let's put the whole thing here. I started out with this, the first relation that we derived, and I went through this exercise and I arrived at that. If instead of starting from the first relationship, I start from the second one, remember the second one is here, has dH instead of du, In fact, I guess that's the only place I wrote it. So if I start with this one instead of with that one, then I will get something similar. But I won't do it because it's a similar development. So you will get that the change in entropy is going to be Cp natural log T2 over T1 minus R natural log P2 over P1. So that's starting from the second one. Because it is dH, that's why there is a Cp, because dH is Cp dt. And because it is actually pressure here that is differential, dP, that's why we end up with when we integrate with a natural log of P2 over P1. So for an ideal gas, I have two equations that I can use. Any of those two, depending on what you have. If you have the temperature and the volume variation, you can use the first one. If you have the temperature and the pressure variation, then you can use the second one. Of course, they must both give the same result, because in both cases, we're just computing the change in entropy, right? So we have those two that are very useful in problems involving ideal gases. And let me show you, if I take it one step back, okay, so in this last expression, I have made the assumption that Cp is constant, just like I did here. So maybe you're going to put that here so you don't get confused. This is for constant Cp. All right? This one. If I take it one step back before I make the assumption that Cp is constant, what I would really have is an integral here. I would have an integral from T1 to T2 of Cp dt over T. And of course here, because R is a constant, that would always be R natural log P2 over P1. So this is one step before I make the assumption of constant Cp. And the reason I'm telling you this is because this quantity, this integral that appears here, is tabulated, so that you don't have to make the assumption that Cp is constant. Okay. So the integral from 1 to 2 of Cp dt over T is tabulated and we can call it S2 super zero. That's just to make a distinction, because this is not the entropy change, it's just one term, S1 super zero. Whatever this integral turns out to be, we call it delta S super zero, or S2 super zero minus S1 super zero. Just because that's the name of the function that is tabulated. And of course, the tabulation is in terms of temperature. So let me show you what it actually looks like in a table that you have already used before. Here's an ideal gas table that you may have used already in some problems. Ideal gas properties of air. Remember, U and H are only functions of temperature. So if you know the temperature, you enter the table with your temperature. You can find the internal energy and the enthalpy. But you can also find this so-called S super zero function. So it gives you a number, the last entry. Never think that this is entropy. So if you're doing a problem and you need to find entropy, never come here and tell me, well, the entropy of air at 340 is 6.99, because that's not the entropy. That's what the super zero is there for, as a warning that that's not the entropy. That's this part of the expression that gives you the entropy change. But you can do that, read that quantity, and don't have to make the assumption of constant CP. So it kind of gives you two ways, two paths to solve a problem involving ideal gases. Either you make the assumption that CP is constant, or if you have the table, then you can do it with the table. We'll do an example later on, and I'll show you the difference between doing one way or the other. Any questions up to this point? No? You have a question? Or you're just changing the position of your elbow?
Me?
Yeah.
No, I'm just changing my elbow.
All right. So, okay. In fact, here's an example right now. Let's do an example right now using this. So in this example, we have a cylinder fitted with a piston. There is air in here. There is air in there. And we are given the following data. The total mass of air is 1 kilogram. It is initially at a pressure of 400 kilopascals and at a temperature of 600 Kelvin. We have this air in this cylinder at this pressure. And then we're told that this air is going to expand and what we're told is that it does so adiabatically. So you think of it that you have this whole system insulated. Right? So no heat transfer comes in or out. So expands adiabatically. And we're told that also reversibly. Okay? So it expands adiabatically and reversibly. So we know it's an ideal process because it's reversible. And it does so until the pressure drops to 150 kilopascals. So it expands adiabatically and reversibly to a pressure P2 of 150 kilopascals. Right? That's what we know. And we're asked to find the work. So find W12. Right? Okay, so we don't know you don't even know the path that the system follows. We know that the pressure is dropping from 400. So for example, if you make let's say that we make a PV diagram to help us understand what's going on. What we know is that it's expanding. So it starts from a low volume and high pressure. So maybe just put it here, 1. This is 400 kilopascals. And it's going to expand to 150. So it'll be larger volume, lower pressure. We don't really know what path it follows. And we cannot make an assumption as to what path it follows. So we cannot use any of our previous techniques to, for example, we could say, well, let's find the work as the integral of PdV, because we don't know what the function is. You know, if we knew the function, then we can find the work quickly, because we can just integrate it or find the area under the curve, but we don't know that. So we have to take another path. Okay, so what is that other path? Well, we know we have new tools that we've learned. For example, because it is adiabatic and reversible, what can I conclude? Because it's adiabatic and reversible. Yeah, in a way, but that's not the word we're looking for. Yeah? Change in entropy is 0. It's isentropic, right? So this, let's label this 1, because I don't have any room there. So 1 implies that is isentropic. How do we know that? Well, all we need to do is go back to what we were just doing. Take a look at, I wrote this here, right? If a process is reversible, this case also, we did this on Tuesday. If a process is reversible, delta Q is TdS. But I'm told it's adiabatic, so delta Q is 0, therefore ds is 0. There is no variation in entropy. So, all right, very good. So if I know that, I can now go ahead and write the, for example, write the first law. Right? Which tells me that delta U is Q12 minus W12. That's the first law. But I'm told it's adiabatic, so I go ahead and cross that out. But now this is telling me, well, I could use this to find the work. Because if I solve for the work, then work from 1 to 2 is just delta U. So all I need to find is delta U, which of course is U2 minus U1. And in this case, the mass is constant, so the mass and was given. So this is M U2 minus U1. So I know that I could get the work this way. Look how it's so completely different from the way you got used to computing work, because you did the integral of PDV. Yes, sir? What happened to what? I forgot about it, didn't I? So what happened to the negative sign? Let's put it right there. All right? So, but the point is that I want to find the work, and I'm going to do it in a completely different way. I need to find the variation in internal energy. Right? Can I do that? Well, I know, can I get U1, the initial internal energy? Yes, how? I have the temperature, and I just showed you a table that, for example, the initial temperature is 600. I can go into this table and read U1, which is 435.1. So I know that U1 is 435.1 kilojoules per kilogram. But I don't have U2. I would need to know the final temperature, so I can go to the same table and read U2. But I don't have the final temperature. So what can I do? Well, here is where I can use this, because I know it's isentropic. So if we go back now to this, right? And for example, I look at this expression here. Let me rewrite this expression here for this problem. So we know that delta S is S2 super 0 minus S1 super 0 minus R natural log P2 over P1. Right? So I take that from there, and I write it here. Remember, this was the integral that is now written in terms of this function. But I know it's isentropic, so I know this has to be 0, because it's isentropic. Right? So, and I know the pressures. They were given to me, P1 400, P2 150. So this part I know, and the gas constant, I have it, is air. So the only thing that I don't know here is S2 super 0. So let's solve for it. We get S2 super 0 equals S1 super 0 plus R natural log P2 over P1. How do I find S1 super 0, the same table that I just looked at? So at the initial temperature, which is 600, let me blow this up so you can see it. 600. I just read this U. Skip 1, which is H. Now I have this 7.576. 7.576 kilojoules. This is huge right now. Kilojoules per kilogram Kelvin. That's S1 super 0. So I can put all of that in here. My S1 super 0 from there. The R I know is air. And natural log P2 or P1, I have everything. So I can compute that number. And I should have it. That number comes out to be 7.295. Kilojoules per kilogram Kelvin. So now I have S2 super 0. So what I'm going to do is I'm going to go backwards in the table. I'll go to the same table and look for a S super 0 that is 7.295. So there is a 7.2 what is it? 7.295. So it's between these two, which means that it is between 440 and 460. Okay? I have to interpolate between 440 and 460. And if you do that interpolation, so interpolate between 440 and 460 Kelvin. And then you get 457. So T2 is 457 Kelvin. All right? So now I have the final temperature. And now that I have the final temperature, what do I need to do? Go back to the very same table. In fact, I could have skipped the interpolation to find the temperature, because the temperature is just an intermediate step to what I really want, which is U2, right? So what do we say, 457? So the U is between 315 and 330, a lot closer to the 330. And again, if you do the interpolation, you find about 328 kilojoules per kilogram. So now you have your U2, and now you can finish the problem, because after we flip the sign that he caught over there, we get W12 is M U1 minus U2. Right? They're flipping the sign. So but everything now we have. We have U1, we have U2, and the mass was given. It was only 1 kilogram. So now we can plug everything in and get that the work is 107 kilojoules. Right? So the only way to do this problem is by using both first and second law. You could not possibly solve this problem without knowledge of the second law, because you don't have enough information. And again, we don't know what this path was. It's a big question mark. But we have the work, right? Any questions? Okay. So let's stay on this topic, which was this process was isentropic. We used that piece of information that the process was isentropic to do the problem. But now let's try to generalize what happens in an isentropic process. So let's call this isentropic process of an ideal gas. So stay with ideal gas. And let's see what happens if you have an isentropic process. So I think I have these ones nicely written, so I don't need to rewrite. I'll just show you. So here's where we are. Maybe I need to make it a little bigger. So we want to know something about isentropic processes of ideal gases with the assumption that the Cp and the Cv are constant. We are going to make that assumption. So Cv and Cp are constant. So let's write down what we know. Many of these things are repetitive, so we've seen them already. Reversible, because we want to make it isentropic, so it's adiabatic. I'm sorry, it's reversible. It's not necessarily adiabatic. It's reversible. So ds is delta Q over T. We know that. If we, like in the previous example, if we make it both reversible and adiabatic, then it's isentropic. So we're going to make that assumption that it's isentropic because of both is reversible and adiabatic. So if we assume that the Cp and Cv are constant, then we have those two expressions, which you already have in your notes. I wrote these two expressions earlier today. So remember, they came from the thermodynamic property relationships to find the entropy change for an ideal gas. We have those two already from before. So, but now what is new is that we're saying we're going to limit ourselves to isentropic processes. So that's why I'm setting them equal to 0. Right? And if I set them equal to 0, then I can manipulate them a little bit to come up with expressions that are a little more compact than these that have the logs. So take the first one, for example. If you set it equal to 0, then you can use properties of the natural logs to rewrite it like this. Remember, there is a property that the exponent becomes the factor in front of the natural log. So all I've done is I've moved the factors and made them exponents. And now I use another property of the natural log, which has to do with the product. So the natural log of A plus the natural log of B is the natural log of A times B. Right? That's what I've done here. And of course, if the natural log is 0, the argument must be 1. So that's how you get rid of the natural log. So you can write then this relationship right here, okay, by manipulating the property relationship for an isentropic process. Okay, what else can we do? Well, you remember this from a while back, that Cp minus Cv was R. I think I can make it a little smaller and you can still read it. So now we're just going to define a new quantity, K, which is nothing but the ratio of the specific heats. Okay. The ratio of the specific heats, Cp over Cv, we call it K. So we do that. We introduce this K, and then we can arrive at this expression here. Again, if I can fit, yeah, I can fit the whole thing. It came from here by manipulating it a little bit using properties of the natural logs. So there is nothing really different between this and this, except that it has been written in a more useful way. So we get that. Remember the conditions that we imposed during the derivation. So that's why I wrote them here. So whenever you write an equation, make sure you know what the limitations are. So it's valid if the process is isentropic, an ideal gas, constant specific heat, Cp and Cv. So we get that. Likewise, I can take the second one. This was all from one, from the first relation. Likewise, I can take the second one and do something very similar. So if I take the second one and I do something very similar, I arrive at the second red box there. So now I took the second one, combined the terms inside the natural logs to to get rid of the natural log, and then you arrive at this one. So these two expressions in these two red boxes have the same limitations. It has to be isentropic. It has to be an ideal gas that has constant specific heats. Right? And there is yet one more, even though we only had two relationships to start with, there is a third one that we can derive by simply combining these two. So realize that both of these have the ratio of the temperatures on the left-hand side. So they're equal to each other. Because T2 over T1 here, T2 over T1 here. So I can just set them equal to each other and get a new one, which is that one right there. A third one. So that's three boxes. They all involve the properties P, T, and V, which we already seen appear many times in ideal gases in the ideal gas law. The last one is perhaps the most common one. It says P2 over P1 is V1 over V2 raised to K. Remember, K was the specific heat ratio. Why is this one the most common one? Does this one ring a bell? Let's rewrite it like this. Let's rewrite it like this. Same thing, I just move things around so I have all the state 2 on one side, all the state 1 on the other side. So it's telling me that P2 times V2 to the K is equal to P1 V1 to the K. So for the initial and final state, that quantity is the same. So I can write that, PV to the K equals constant. So that rings a bell, should ring a big bell, which is? It rings the bell of the polytropic process. So, however, there is a difference, right? The polytropic process, remember, I may have written it here, had an N, right? It was P times V to the N equals constant. So what this is telling, and this K is not any N. N could be anything, remember. N could be any number, right? Any real number. This one has to be K. So this expression in the red box is valid for an isentropic process of an ideal gas with constant Cp and Cv. And it happens to be a polytropic process for which N is equal to K. So conclusion is that for such an ideal gas, an isentropic process is a polytropic process where N is the ratio of the specific heats. This also allows us to summarize what we know about polytropic processes. So let me move this away and show you this graph. Here is a graph of polytropic processes plotted on a PV diagram for ideal gases. And you can see the different scenarios. Some of them we have looked at before. There's one that was a question on the exam, on the midterm, right, which was for an ideal gas. If it's isothermal, what's the N? Remember, that was a question on the exam. The answer was N is equal to 1. Because for an ideal gas, PV equals RT. If it's isothermal, then PV is constant. That means that the N is 1. But here you have all of the possible scenarios. So there is that one, isothermal, T equals constant. The other two very common ones are N equals 0 and N equals infinity. Right? N equals 0 gives you P equals constant. So that's isobaric, N equals 0. N equals infinity gives you V equals constant. So it becomes isometric. And here is our isentropic process. When N is equal to K, that's this one. That's the isentropic one. Most common substance that you should know what the K is air. Does anybody know what the ratio of specific heats for air is, Cp over Cv? Anybody? Nobody? You do? No? Maybe? Any guess? It's not 1. That would imply that Cp is equal to Cv. Right? And remember, Cp minus Cv is R. So obviously, it's not 1. Okay? Is it greater than 1 or less than 1? It has to be greater because Cp is larger than Cv. Well, for air, it's about 1.4. So write that down. Cp of air, 1.4. Okay? The ratio, I'm sorry, not Cp, K. K of air is 1.4. I should write it here. K for air, 1.4. That's why the slope of that curve is a little steeper than the slope of the isothermal process, which is n equals 1. This is 1.4, so it's a steeper.
So are we treating air as an ideal gas?
Yeah, this is looking at air as an ideal gas.
Okay. Isn't it for a polytropic process, though, K would be 1, so N would be 1?
For a polytropic process, no, only if it's isothermal, right? If it's isothermal, remember that comes about from PV RT. So if it's isothermal, then it becomes PV equals constant, which means that N must be 1, right? But these are all kinds of processes. You can put any process here. We're just showing you the most common ones: isobaric, isometric, isothermal, isentropic. There is another one here, the N equals minus 1. What would that be? If it is a spring, right? If there happens to be air in a process where there is a linear spring, then you would have that, for example. Okay, any questions? No questions? Let's march on then. So another thing, these are reversible processes. We should be concerned with real processes. So real processes are, of course, irreversible. So let's look at what happens if you have a real process. I'm going to go over this. Maybe I'll go ahead and do this longhand because it's important. So let's see what happens if you have an irreversible process. So irreversible. Real, right, process. How will the story change? Because everything we did for this portion of the lecture was reversible, it was isentropic. So we're going to do it the same way we did at the beginning of the last lecture. So I'm going to have an arbitrary process that is going to take me from state 1 to state 2. You might recall I did this last time. I said I'm going to go from 1 to 2 on one path that I call A, and I'm going to come back on another path that I will call B. I did that last time, and I said these two are reversible. And so that's how we did. So let's say A, let's write here, A is reversible. B is also reversible. So this is just like last time. And remember, we know this since this is a cycle, and it's reversible, what is this equal to? Loud. 0, right? It's a reversible cycle. The classes inequality, that's the one case where this is equal to 0. And what we did last time is we broke this down into the two segments. So we say from 1 to 2 on path A, delta Q over T, plus integral from 2 to 1 on path B, delta Q over T. Just like we did last time. So far, the same as before, nothing new. And there is nothing irreversible yet, so we'd have to do something irreversible. So let's change the going process. So instead of going on A, which is reversible, we're going to actually go from 1 to 2. Do it in another color here. From 1 to 2, I'm going to take another path, C, and this is the irreversible path. That's a real process. But I'm still going to come back on the reversible one. So I'm going to go on C and come back on D. So when I compute this cyclic integral for this process, is going to be the integral from 1 to 2 on C of delta Q over T, plus this last one is the same because I'm returning on the same path. So 2 to 1 B delta Q over T. All right? And what do we know about this one? What is this equal to? That's a tricky way to ask the question. It's less than 0. We don't know what it is equal to. We only know that this one has to be less than 0. Why? Classes inequality, because there is an irreversible part that throws off the classes inequality to the irreversible side. So even though one of the two paths is reversible, the fact that there is an irreversible path makes the whole process irreversible. It just takes one portion to be irreversible to make the whole cycle irreversible. So I get that. So while the first one is equal to 0, the second one has to be less than 0. But if you now look at this and compare, what do we conclude? Because this is the same. But this is not the same. And this whole thing is less than 0. Huh? So what do you conclude? You agree with me that you have to conclude that this one has to be less than this one? Right? This part is the same. This is 0 and this is less than 0, so this has to be less than that. Okay, so what is that telling me? And these two, the difference between these two is that this one, the one on C, is irreversible. Huh? And the one on A is reversible. Right? All right, so the integral has a smaller value in the irreversible process. So what does that tell me? If I write it in differential form, let me take this, let me leave that there. For path A, for path A, which is reversible, I know that the integral from 1 to 2 on path A of dq over t is equal to what? But what is this equal to? No, but for any reversible process, what is this equal to? Not 0. It will be 0 if it's a cycle, but it's not a cycle. Go back to this. For a reversible process, delta Q is TdS. So divide by T, integrate, that's delta S, the change in entropy. So this is the change in entropy, right? S2 minus S1. Right? And we know that the integral from 1 to 2 on path C is less than that. Right? We concluded that right here. This is less than that one. This one is the change in entropy. So this has to be less than the change in entropy. Right? So the integral calculated on the reversible path, on the irreversible path, on the real path, is less than the entropy change. So if we put it together, then using this one, what do I need to do to make this an equality? So this is what we have. Let me write it the other way. So delta S greater than integral from 1 to 2 on path C of delta Q over T. If I want to make an equality of this, where do I add something? On which side? On the right-hand side. So if I want to make this an equality, I have to add something here. Okay? Then it becomes an equality. Well, it turns out that that something is always going to be a positive quantity. Right? And there's never going to be a case where I have to subtract. It's always going to be a positive quantity because the second law tells me that the total change in entropy is greater than what I calculate from the integral here. So this is then a crucial quantity in thermodynamics because this is what we call entropy generation. The thing that I need to add to make the equation an equality is what we call entropy generation. And very important because the other paths, A and B, were ideal paths. They were reversible paths. This was a real path. So this is a real process. So any real process will have entropy generation. Absolutely every process. So every process that takes place generates entropy. Every process that takes place. So that's why you may have heard that an expression about the entropy of the universe is always increasing. Have you heard that? It's always increasing because all processes generate entropy. It's always increasing, increasing. It never, if you take the universe as a whole, then the entropy has to go up all the time. There is no way for the entropy to go down because the second law of thermodynamics tells us that there is always entropy generation. So you want to write that there. So this is always positive. There is always generation of entropy. Any questions? Let me see. I want to spend about I have time, so I want to do another example using this. Any questions? We'll probably do one example in about 5 minutes, so that'll be it. So I borrowed one example from the midterm. I changed it a little bit and added something. So you remember the midterm problem of the tanks. There was a membrane, tank A, tank B, or side A, side B, same tank. And the membrane disappears, the gases, it was air mix, and I think you were given the final temperature and you were asked to find the final pressure and a couple of other things. So I changed it a little bit. The start is more or less the same. So I have information on each tank. So for each side. for side A, in fact, I use some of the same numbers, is 1.2 cubic meters. It's 200 kilopascals, and it's 40 Celsius. Those are the same numbers. And for B, it was 2 cubic meters, 100 kilopascals, and 10 Celsius. So in the exam, you were told the membrane disappears, the gas mixed, they come to an equilibrium temperature which was given, right? And you were to find then the pressure. And you also had to find the heat transfer, if there was any heat transfer coming in and out of the tank. So I'm going to change it. I'm going to make this tank perfectly insulated. So there is no heat transfer. So, and instead, I'm going to ask you to find the final temperature. Right? So find T final. Find the final pressure. And tell me if this is a reversible or irreversible process. Okay. So rev or irrev. Is it ideal or real? Okay, first part proceeds more or less the same way. If you did it right on the exam, first thing you probably had to do was to find the mass, because you knew you had enough information. So using ideal gas law, you could find the mass. You have the initial pressure, the initial volume, the initial temperature. This is air. And the universal gas constant and the molecular weight was given. So, to make a long story short, you could get the mass in each tank. And 267 kilograms and 246 in one version of the exam. All right? So now, now we have to find the temperature. And we're told it's adiabatic. But we're not told that it's reversible, so we're in fact to find out. But we know it's adiabatic. So if we write the first law, and we take the whole of the inside of the tank as this, our system, all of the air is our system, is adiabatic, and there is no work. Right? So in this case, then the total change in internal energy must be 0. Right? So what does that mean? Well, of course, that means that U2 has to be equal to U1. And what is U1? Well, U1 would be the mass in one tank times the internal energy in that tank, the other tank, internal energy of the other tank. I could do that. And I can do the problem two ways depending on what I have. If I have a table like the one we were looking at, if you have this table, since I have the temperatures, I can read the U's, and then this is, of course, the total mass times U final, right? That's the U2. So I have the masses. I can read the UA and UB, total mass, solve this equation for U sub F, come back to the table and find the final temperature. That's one way I can do it. So via table. Or I can do it via C sub V. If I have the C sub V, which was the case in the exam, C sub V was given. I can just replace the delta U's with CV delta T's, and I can also get the temperature that way. So you can do that. I did it this way, via C sub V, and I got a temperature of 26 T final 26 Celsius. Right? I'm not going to do that part because you should not do that part, but I'll just tell you that you can go either way. All right, so now that I have the final temperature, I can get, so I have answered this question. I can get the final pressure using the ideal gas law. So PF, P final, or P2, whatever, either way, is going to be total mass, R, T final, over total volume, which is the sum of the two volumes. So this is also straightforward. Can do that and get your pressure 138 kilopascals. So now comes the final question, which is this process reversible or irreversible? What should I find to see if it's reversible or irreversible? If it's irreversible, what happens? There should be what? Sorry? If there is no change in entropy, that makes what kind of a process? Reversible, right? So it actually goes back to this very last equation. Okay? So this path C was a real process. So this is for a real process. You can put that there. So I already know it's adiabatic, so this term is 0. It's adiabatic, so I can cross out that. So what I have is that if there is an entropy change, it's only due to entropy generation. In other words, if I find that there is entropy generation, or if I find that there is an entropy change, then that makes the process irreversible. So that's what I need to do. So what I did, what you can do is go back to any of the equations that we derived for an ideal gas today. Let me just show you one, if I can find it. One second. One of the all right, so here, this first equation on the top, right, allows me to find the entropy change if I know the pressure variation of the system, the temperature variation of the system, and the CP and the R. So which we're going to assume that we have the CP, it's air. So it looks like I have everything. The only complication is that there is this mixture. The system is initially segregated into two parts, and then it mixes. So I have two initial pressures. I have two initial temperatures, even though the final pressure and the final temperature are the same. So that's the only tricky part. And so what you have to do is then, let's continue here, carefully compute this delta S. So we know that delta S is S2 minus S1. Every time you have a problem in which the masses are initially separated and they mix, or they essentially together and they separate, you have to be very careful. So you know that, and then you go in order. You say S2 is M2, little s2, and this S1 is made out of two parts, so that's where you have to be careful. So you say, well, the S1 has an MA SA and an MB SB. Okay? The two segregated initial masses. And of course, this M2 is MA plus MB, because that's the total mass. So I can write this as MA, right? S2 and SA, right? So I combine MA, S2 minus SA, and then the M2 is as also plus MB. So treat that separately, MB, which multiplies S2 minus SB. That way you have segregated the variations. So now you have MA, S2 minus SA, MB, S2 minus SB. Right? So now you can deal with the different initial values. And of course, you still use this expression for each of the delta S's. Right? So this is the delta S for A, and this is the delta S for the B mass. You compute them that way. But you have everything, because now you can go separately with each A and B into this equation and plug all the numbers in. And if you do that, you find the first part, well, I have the total actually. But the interesting thing is that one of them is positive and the other one is negative. But the end result is positive, which is what really matters. So the end result is, if you want to do the numbers later to check, you get 0.072 kilojoules per Kelvin. Right? And it is positive, which means that the process is irreversible. Right? So it's a real process in that regard. If you had obtained 0, then you know the process is reversible. Right? What happens if you get negative here? It means that you made a mistake somewhere or the data of the problem is wrong, because it would imply that there is negative entropy generation, and that's impossible. All right? Okay, so I'll see you next week.